everybody able to see my screen?
Yep, you're good.
All right, great. All right, so as Matthew said, my name is Kirsten McMichael. I'm a PhD student at Rensselaer Polytechnic Institute, and today I'm speaking on behalf of the NEST collaboration. I will be talking about physics modeling of xenon and argon detectors with the noble element simulation technique, otherwise known as NEST. So what is NEST? At its core, it is a C++ package with a Python equivalent that has been named NestPy. It has optional Geont4 and root integration, and it simulates the scintillation, ionization, and electroluminescence processes in xenon and argon. It is openly available on GitHub, and I have linked in my presentation where you can download it. And for comparison plots or to just learn more about a collaboration, I've also linked our collaboration website. So who is involved? NEST is kind of a collaboration of collaborations. So various academic institutions that have listed on this slide, as well as members of LUX, LZ, Xenon, Nexo, Coherent, Dune, Icarus, just to name a few. So we really have across the spectrum people contributing to NEST at all times. And so some of the features of NEST, the models themselves use a combination of both empirical and first principles methods. It is very customizable in the sense that you can input custom detectors to really tailor it to your experiment, and it is very fast. That was probably what I noticed most when I first started using NEST was you don't need this supercomputing power to get these calculations done. You can run it on your desktop, and depending on what you're trying to complete, it's on the order of seconds or minutes that you get a result. Models for various types of energy deposits are available, including electronic recoils, nuclear recoils, alphas, and it calculates average light yield, charge yield, and recombination, and is able to simulate actual energy deposits within a detector. So now I'm just going to kind of go through some of our plots and some examples of what NEST can do. So on the xenon side of things, we first have nuclear recoils. It is able to model both the light and charge signals, as well as the amount of energy lost to heat. These are our light and charge yields. For NR shown here, the three dotted lines is NEST NR models for both 50, 200, and 2000 volt per centimeter fields, and then various data sets showing the very good agreement. For the ER models in xenon, we have beta and gamma models that fit data ranging from sub-keV all the way up to MeV energies. And shown on this slide is a beta model for both the 150 and 200 volt per centimeter fields. You'll notice that the shape wiggles as it passes through both our Thomas Amell box and Doke-Burke's regimes of our model. This is something I can probably get into more in the questions later. The energy resolution for xenon. So on this slide, we show that there's excellent agreement with xenon 1 ton at both high and low energies. On our left plot, it's a 2.5 MeV resolution in liquid xenon from NEST versus G1, and the different colors are just different fields. So we're seeing a really nice agreement with that black dot from the xenon 1 ton measurement. And then on the right, we see our low energy argon 37 peak. So the black line, dashed line is the xenon 1 ton calibration data. We have the NEST simulation, which is us plugging in the exact parameters from xenon 1 ton in the detector file. And then we have a fit where we're showing really strong agreement. And it's very important to note that part of the reason we can get such a good agreement is because NEST does also account for skewness in its modeling. So recently, NEST has also not taken its focus from not just xenon to also now argon modeling. The argon nuclear recoil model is now fully implemented in the main NEST code, and it's available if you download the most recent version of NEST. And it's built using various data sets from SCENE, ARIS, DS50, and among others. And so on the bottom plot, we see total quanta versus energy, and we're seeing NEST in the black line fit to the data, and it is once again showing that it's fitting the data very well. On the top plot, we're seeing S1 and S2 peaks for a 16.9 keV nuclear recoil and liquid argon. So the NEST simulation is shown, it's kind of hard to see on these plots, but it's the light gray lines and then also light gray dashed lines. So the dashed lines are NEST with a 20% noise. That's where we see the most or best agreement, but this noise level is very compatible with what was assumed in SCENE. So we're very happy with those results. And then on the ER side, for argon, that is also now published in the NEST code based on world data. The model is still being finalized, so we're hoping for a final stable Burks-like model for both high and low energies. Right now, the current version works very well for low energies, but we are still, always trying to be perfectionists, so looking for some improvements in the high energy regime. Myself personally, I am a member of the Nexo collaboration, so I've been very interested in some XO 200 results. So in 2020, XO 200 reported a discrepancy between their W value and the NEST value. So XO 200 reported a W value of 11.5 EV, whereas the NEST W value in 2020 was seeing 13.7 EV. This wasn't really a surprise, as NEST at the time had been very fitted to the dark matter experiments, and the 13.7 was matching that of Lux and Xenon. But obviously, as an XO 200 collaboration, you want to have NEST models simulating your models as well. So what we think is happening there, a potential option is potentially that IR photons are a potential culprit. This would be something that the XO 200 detector would have been very sensitive to, but dark matter detectors would not see. And that being the case, we're currently taking this tactic that, okay, well, if it's just that the detector's not seeing it, then it's probably something that's always physically present, but just not always captured. So we've introduced what is now in NEST called the remove quanta flag. So if you are a dark matter experiment, and when you download NEST itself, it is set to on. And so basically what we have is inherently in NEST, we have this excess quanta being put in, but with the remove quanta flag turned on, you are then blind essentially to this extra quanta. And we have verified that by doing this, all Lux and Xenon 10 data still matches. We're not messing with any yields or anything. So those dark matter for folks are safe. But also if you're an XO 200 or nexo or neutrino fan, then we are now seeing, if you remove quanta off, that we do see the 11.5 EV W value. And we've also now seen obviously an increase in our light yield for trying to match XO 200. We are still trying to mess around with the field dependence to get an exact match for light and charge yields for the XO 200 data, but that is something that I'm currently working on and we hope to have out very soon. So just to conclude, NEST models the intrinsic physics of noble detectors while maintaining a format that is both accessible and customizable for its users. And we have many recent and upcoming changes, including improvements to the liquid argon ER model, improvements to the liquid xenon ER model, gamma calibrations, W value agreement with XO 200 results, and noise. So that concludes my talk for today. I would be happy to answer any questions if anybody has them. Thank you.
Thank you, Kirsten. You ended early, actually 2 minutes early, so we have plenty of time for questions.
Good.
So if you have a question, please raise your hand so that I can call upon you. Any questions?
I'll ask one. For this IR photons, is there, I guess, is there a mechanism that you're moving towards attributing these IR photons to?
So yes, but it's something that we're definitely looking into right now. So my advisor and I are currently actually digging through the chemistry papers to kind of figure out exactly what this mechanism is. We think it could have something to do with Excimer states, but again, we're still very early in trying to decide exactly what this process is.
Thank you. Next question is from Paula Ferrario.
Yes, I wanted to ask if there has been any progress on simulations in the case of zero electric field that I was interested in some time ago.
So I personally haven't done work with that. I might cheat and say Matthew, for those who don't know, Matthew has created the NEST code. So is there any input from you on that as far as what NEST has been doing?
Yeah, no, I'm afraid that the status is still the same. Like it's there and it's available. It's not any better or more precise than it was before. And the reason is because most of the people on NEST, we have non-zero field. People work on non-zero electric field TPCs. But if we could recruit more people who work on zero field, we'd be happy to expand in that direction if it's needed for the community. But it does work. It's just not as outstanding as the other parts of the code. But there's definitely what we have is the same thing we had before.
Yeah, okay, thanks.
Matthew, I want to just add a comment that the nest is always have a zero. If you extrapolate down to the 0.1 volt per centimeter, that's zero field. And we didn't have much data for low field. That's why we cannot, not well trust this extrapolation. But from this conference, we just heard that the Heidelberger xenon detector measured some low field data. We could use this data to further fine-tune this nest model down to zero field.
Absolutely. We're always updating. Any other questions, though, for Kirsten? I see another hand raised. Yes, Christoph, please, go ahead.
Yeah, so maybe this is a bit naive, but the software works for xenon and argon. Could it also work for xenon-doped argon?
So I guess, again, Matthew, feel free to jump in, but I would say my initial thoughts would be if we have the data available and NEST is doing a lot of matching to empirical results, and I would say in theory, yes. But Matthew, I don't know if you have a differing opinion on that.
It would be hard work because we're using empirical models. The thing with doping is you need to focus more on first principles because you have individual atoms floating around. So it could be doable, but it just like with gas and with zero field and the other parts of NEST would require more people and more effort. But yeah, so don't see any reason why we couldn't do that in the future, of course.
I see. Thank you.
We still have time. Are there any other questions for Kirsten? All right, seeing no other questions, thank you so much for your talk.
Thank you very much for listening. Have a nice day.
All right, so our next speaker is Olivia Piazza, who will be discussing a first principles approach to electron ion recombination in liquid xenon.
Hi, everyone. All right, so I'm Olivia Piazza. I am working with a liquid xenon group in UC Berkeley with Vetri Valon and Dan McKinsey. And we were interested in studying recombination and recombination of fluctuations because we know they affect detector sensitivity in liquid xenon TPCs. What we don't know is the underlying physics of how this happens. So to better understand this, we developed a first principles approach to electron ion recombination in liquid xenon. Sorry, I forgot to turn on my video. And we did this by carefully considering the kinematics, electrodynamics, and nuclear interactions of particles within liquid xenon systems. So I assume most of you are aware of this picture on the right. In liquid noble time projection chambers, signals are generated in two forms, and those are ionization events and escaping electrons, leading to S2 signals, whereas photons released in recombination of electron-ion pairs and the de-excitation of dimers creates the S1 signal. We can derive whether the energy deposition event is from an electronic or nuclear recoil based on these signals. And recombination is known to vary as a function of energy and field and affects our ability to discriminate between electronic recoils and nuclear recoils. While there are various empirical and theoretical models that attempt to explain this recombination probability distribution, none do so for the full energy range, and none explain recombination fluctuations. For this particular study right now, we were interested in dark matter energy ranges of about 15 keV and below, and so we focused on that for figuring out the physics of recombination fluctuations. The plot on the far right was produced by the Lux collaboration and shows the variance of the electron recoil band as a function of S1 signal. This variance corresponds to the width of the blue region in the plot to the left, which I also assume most of you have seen before. And for this plot on the right, the solid line at the top represents the total variance. The bottommost trace is the smallest contributor and is attributed to fluctuations in total number of quanta present in the system. Immediately above it are fluctuations from the S2 signal, which are the dotted lines. Then above that are the fluctuations from the S1 signal, which are the dashed lines. Just above that and immediately below the solid line is yet another dashed line showing that the electronic recoil variance due to fluctuations in recombination is the greatest contributor to electron recoil band variance. And it's much larger than the binomial fluctuations. So in response to this outcome, we decided to build our simulation and explore whether there was some interesting physics underlying the recombination fluctuations. The simulation begins by setting a value for the primary event interacting with the liquid xenon and an external electric field value. There are no geometric boundaries, meaning the physical space of the particle interactions extends to infinity. The primary event is then sent through the liquid xenon in a random direction and allowed to interact with the system. It does this by randomly sampling several distributions on whether the primary event will induce an ionization, elastic collision, excitation, or not interact at all at some time step. After determining what the interaction event will be, the appropriate cross-section is sampled and the maximum collision rate is determined based on the energy of the primary event. From this value, which we called Kmax, the mean collision time is calculated, which is the average time taken for a particle to interact with the system. A time step is randomly sampled from this mean collision time, then the particle is allowed to propagate, updating the position and velocity, as well as any forces that might be acting on the particle, like Coulombic or external field forces. If an ionization occurs in this time, a new electron and ion pair is created, and the new electron's interactions with the system is tracked. After the interaction step, the primary particle then loses some energy, and the particle is checked to see if it meets some recombination or escape criterion. To recombine, the potential energy of the electron to the closest ion must be greater than the electron's kinetic energy. To escape the system, the electron must be some distance Rmax away from the closest ion. If the particle escapes or recombined, it's tagged as such and then removed from interacting with the system. The simulation continues until all particles have either recombined or escaped. This simulation was built in Python and it can be run on a local machine. It's better suited for a distributed computing cluster, but it just takes a little longer if you run it on a local machine. Data collected was based on 1,200 simulation runs for each primary energy event and electric field value. These cross-sections shown were generated using data supplied by the Nuclear Data Service Group. These cross-sections consist of elastic collisions, excitations for different orbital interactions, and ionizations. I also generated the liquid elastic cross-section in orange using a structure factor, which I'll talk about next, and the gaseous elastic cross-section from the Nuclear Data Service Group, which is the dotted blue line. At energies above approximately 0.5 electron volt, the liquid xenon effective elastic cross-section and the gaseous xenon elastic cross-section are equal. The energy loss per collision for this effective sigma is assumed to be proportional to the relative velocity of the electron-ion interacting pair. So key to this simulation, we utilized the Cohen-Lechner theory of hot electrons. In the context of this simulation, it's important to emphasize that this theory only applies for elastic cross-section collision cross-sections below 1 electron volt. For higher energies, the Nuclear Data Service Group elastic cross-sections are used, and in this theory of hot electrons, Cohen and Lechner assume that the liquid xenon forms a semi-organized structure creating a liquid lattice. Because of this structure, there's a structure factor introduced that allows electrons of higher thermal energy than the surrounding liquid lattice to travel a further distance from its parent ion before thermalizing. As shown on the left, the elastic collision cross-section is scaled by the structure factor and is constant for energy below 0.6 eV. For this simulation, the cross-section of the structure factor was fine-tuned up to within theoretical uncertainty. Generating time steps are worth brief mention since it's vital in capturing the dynamics of the system. The time step, as previously mentioned, is generated by determining some Kmax factors shown in the plot. to the right, and then taking the inverse of Kmax scale by the liquid density. A time step is then sampled from this and is at most 1.3 times 10 to the negative 17 seconds. This guarantees that the time step is small enough to capture all the system dynamics without unnecessarily slowing down the simulation. All right, so here is an example plot of the simulation output. Pictured are the trajectories of all secondary electrons in a 200 electron volt primary event. The primary event begins at the origin and runs until all particles have either escaped or recombined. The direction of the external electric field is defined to be in the z direction, and delta electrons can be seen drifting in this field. The time elapsed for the energy levels we've been interested in for primary events is usually a few nanoseconds or less within the simulation. Here's another example at a higher primary energy event, 2 keV. And I actually truncated this plot a little bit for the time step because it just drifts for a really long time once it reaches the ends. All right, so here are the results of 1,200 individual simulations calculated for each primary energy deposition labeled on the x-axis and external electric field value, which is color-coded and displayed on the legend. The average recombination rate is then plotted as a function of energy, and as you can see, it has good agreement with NEST. As far as we're aware, and please correct me if I'm wrong on this, this is the first time a recombination simulation matches data from a first principles physics-based approach and has acceptable agreement in both super low energy regimes of about 100 electron volts, as well as good agreement in more empirically supported regimes like 10 kiloelectron volt depositions. Furthermore, this simulation demonstrates W is constant for energy and field within uncertainty and consistent with measured values. When plotting all particles in the simulation that escape versus recombine in the 2D histogram, we produce a slope of -1, which demonstrates all particles in the system are accounted for through either recombination or escapes. And from this 2D histogram, the recombination fluctuations were extracted for all energy values. Finally, the recombination fluctuation was derived by finding the length of the major axis of a fitted ellipse corresponding to 1 standard deviation of particle recombination versus escaped particles, that 2D histogram I previously showed you. This value was then divided by the average number of ions present for each energy deposition and external
Olivia,
field.
1 minute left.
Awesome. As shown on the slide, recombination fluctuations in the sim are demonstrated to be within reasonable agreement of NEST values at energies as low as 2 keV. So, as demonstrated, our simulation has good agreement with NEST, which is an empirically driven framework. Furthermore, our recombination fluctuations are within a reasonable uncertainty of NEST results. Currently, we're investigating the cause of recombination fluctuations by examining the simulated stopping power and geometric properties of the primary tracks. And we're hoping with better physical understanding of recombination, we can suppress recombination fluctuations to enable better background rejection in dark matter experiments. Next, we plan to extend the simulation to higher energies, explore recombination for multiple energy depositions, which was recently mentioned by the Zelda collaboration at Northwestern, who suggested that recombination may not only be affected by the total energy deposition, but the number of tracks depositing this energy as well. We also plan to use this simulation for characterizing recombination fluctuations for liquid xenon dopants such as helium or argon, which may result in faster electron thermalization, shorter tracks, and more recombination. Thanks for coming to my talk, and I'd be happy to answer any questions.
Thank you. Any questions? I see questions going up. Okay, so Austin McDonald.
Yes.
Go ahead.
Thank you, Olivia. That was very, very detailed and thorough. I have kind of a question for my own understanding. Was that you started with the elastic scattering cross section from the gas phase, and you modify it with this this factor. So I always, I've played with some of these models, and I've always never, the liquids in my mind work as kind of a semiconductor, and they don't kind of quite obey the same scattering laws. But you seem to have pretty good agreement if you just multiply it with this this hot electron factor. Is that right?
Yeah, this particular regime we were noticing in the original simulation before we introduced this hot electron factor that the electrons weren't escaping far enough when they first ionized. And so we were noticing that this was on a length scale roughly half of what the ion-to-ion separation was, and we found this paper that Fox did in 2014 with liquid argon, where they showed some success using this method, and so we replicated this method, and it did take some fine-tuning to get that correct structure factor, but it was within a pretty reasonable magnitude of the original structure factor proposed due to the liquid structure of the xenon.
Thank you.
Okay, next question is from Dominic.
Hi. So many thanks for your very interesting talk. Do you plan to investigate the dynamics of your models, so to speak? Because if you think about the difference in the pulse shape for electronical interactions between applying a drift field or not, you see that the recombination affects the pulse shape of the resulting S1 scintillation pulse. Do you plan to check this as do this as a cross check, basically, if your model predicts the correct dynamics?
Oh yeah, absolutely. We're planning on using any. Oh, I'm sorry for the dogs barking in the background. We're planning on utilizing any empirical or reasonably accepted models in the community to cross check this simulation.
Okay, next question is from Austin de St. Croix.
Yeah, thank you. Maybe I missed it, but how do you decide on the momentum transfer? Like, how do you decide how much energy the primary imparts to the electrons around it as you go through these steps?
How do we decide how much energy? Oh, yes, we let me find the slide. How do we decide how much energy imparts? So for the different kinds of transfer structures, obviously, like excitations will impart a specific energy amount, and ions, we assume the literature value for ionization events. But for this momentum transfer, we essentially sample we take a ratio of the mass of the electron versus the nucleus or the atom it's colliding with, and then we sample a cross section for what angle it could possibly collide with and get the energy in that manner.
Okay, so it originally comes from all the cross sections for that energy process. Like you add them all up and then that gets sampled for each step.
Yes.
Something like that.
Yes. And this is just this specific cross section shown is just a subsample of all the cross sections we have. We actually have many more exciton or cross sections that we sample from. So it's a more complete picture in the simulation. It was just too busy to plot.
Yeah. And then what kind of ratio of excitation to ionizations do you get?
What kind of ratio to excitations to ionizations? I mean, it's dependent upon, it's actually not dependent upon this. I don't have it in front of me. I can get back to you on that, but I do have that in the simulation. I just didn't put it in an extra slide. So sorry.
That'd be great. Thank you.
Thank you.
Any other questions?
Can I ask a question? Can you hear me? It's Alexei Bolotnikov.
Yes, go ahead.
Can you apply your approach to simulate dependence of fluctuations on the density? Because as you know, perhaps that there is a strong dependence of fluctuation on the density, and at a certain point it just jump almost like a step function. And if you could simulate this and basically explain why it has happened.
Yeah, right now we hold the density constant. That is something we could explore in the future. And this hot electron theory is very dependent upon having a constant density. I don't think anybody's approached it as a variable yet, but that would be something interesting to pursue in the future.
Because I was always under the impression that fluctuation actually caused not by fluctuation of recombination, but fluctuation of density of ionization, which itself affects, of course, the combination. So, for example, belt electron model can explain all of this, no problems with the xenon, for example. Okay.
Well, Lexi, it may be that the recombination fluctuations are in turn dependent on the fluctuations in ionization density.
Yeah, that's sort of the primary goal. So you need to introduce some kind of mechanism which causes fluctuations, because the combination itself does not give you any fluctuations. But a number of delta electrons produced during the ionization process, it's exactly process which gives the fluctuations. Okay, thank you. Very nice talk. Very interesting. Thank you.
Thank you so much.
Any other questions? All right, seeing no other questions, thank you, Olivia.
All right, thank you. Thanks for having me.
All right, our next speaker now is going to be Jonathan Hefner, talking on characterizing the electroluminescence region of the next high-pressure gaseous xenon TBC using krypton gas. All right, your screen is up. You're good to go.
Okay, great, thanks. So yeah, hi, my name is Jonathan. I'll be talking on behalf of the next collaboration about characterizing the electroluminescence region of the next high-pressure gaseous xenon TPC using krypton gas. So I'll talk a bit about the krypton gas calibration procedure. I'll go a little bit in depth about what that is. I'll talk about some specific detector properties like gap size that we are able to characterize using that gas. And then I'll talk about some interesting work about determining event position from diffusion rather than S1 minus S2. Again, more on that later. So let me talk very briefly about the concept and design of the next experiment. So next is neutrinoless decay, a process that, if observed, would indicate that the neutrino is its own antiparticle. It's a high-pressure gaseous enriched xenon time projection chamber. So many people are familiar with this, but essentially when a particle comes in and hits the xenon, it produces a flash of light that we call our S1, as well as ionizing some electrons. The ionization electrons drift towards our EL region in a constant electric field. The EL region is a much higher electric field, which accelerates the electrons and produces a secondary flash that we call the S2. The timing between the S1 and the S2, along with drift velocity, is what gives a depth in detector. So next has energy reconstruction capabilities using a plane of PMTs and tracking capabilities. We have calibration with radioactive krypton gas and great potential for scalability for next generation neutrinoless double beta decay experiments. So the program began with some prototypes. We just finished running Next White, which was around 10 kilograms. And we will soon be running Next 100, a 100 kilogram scale detector, which is currently under development. And hopefully later a ton scale program. So let me start by talking about krypton calibration, which is sort of the of all of this. Krypton is a gas. We get radioactive gaseous krypton from the decay of radium-83. It deposits fast point-like events at 41.5 keV uniformly throughout our detector. It has a short lifetime and a low energy, which means that there's no long-term calibration that could potentially mess with our sensitivity. Sorry, no long-term contamination. And we are able to calibrate spatial variation and for the finite electron lifetime, which is essentially an effect where when events are deposited deep in the detector, the electrons that are produced spend some time drifting, but may attach themselves onto xenon. And so consequently, events that are deeper have a higher probability of being lost, and so deeper events appear smaller. We have continuous calibration over time, and it allows us to get our excellent energy resolution and improve our sensitivity to neutrinoless double beta decay. So here are some pictures of just the correction maps that we produce. We do an XY correction, which basically accounts for variations in signal in X and Y. And this is essentially the average signal equals 0. Here's a map of the lifetime, which shows how this finite electron lifetime varies over our detector. So here we can see variation. On the plot, we see measured krypton event energy versus Z position with no corrections. And there are two effects that are very clear here. One is that there's a lot of smearing, right? There's spread in the energies. And the second is that there's this consistent downward slope, is what is coming from the finite electron lifetime. When we apply both of our correction maps, it wraps into place, applies nicely along the line to get good energy solutions. 3.8% full width half max energy resolution at 41.5 keV, and many additional studies can be done with krypton as well. We can characterize, time stability variations, different analysis methods, as well as specific features of the detector, such as the electroluminescence region, which will be described in what follows. We can look into effects coming from the gap voltage variation. There's really many, many things that can be done. There's more in the backups. So let me talk now about the characterization of the electroluminescence region. So, as a reminder, the electroluminescence region is where NEXT produces S2 signals. The S2 signals depend on the gap high voltage. So the electroluminescence gap here, it's about a 5 millimeter gap. It's held at 7.7 kilovolts. You're accelerating electrons across it to produce a signal. So the higher voltage you apply across it, the bigger the signal is. Consequently, we are also sensitive to the spacing of the EL gap and the alignment, because if there's an inhomogeneity in the spacing, that leads to an inhomogeneity in the electric field, which feeds into the level of amplification for our S2s, and it could potentially impact the energy resolution. So luckily, krypton is uniformly distributed. High statistics gives us a tool to investigate any of the non-uniforms. So I've put on the left side of the screen here a formula for the total light yield in terms of the EL gap field and the EL gap size. It is maybe a bit intimidating. I mean, it's a formula, but the point that I'm trying to communicate is that along with some known constants and the pressure, the total light yield depends linearly on the voltage that you apply across the EL gap and on the size of the EL gap. And you can see that here. If we fix a single XY position and look at how the light yield varies with EL gap voltage, the yield is linear in the voltage for krypton events. So it turns out that you can get the gap size, D, by looking at the y-intercept of this line, divided by some known constants. If you want to figure out what the constants are, you can rearrange this formula. The point is that to get the gap structure for each position, we can measure the light yield as a voltage. We fit to a line as shown here, and we can get the y-intercept. And then we can apply our knowledge that the gap is proportional to the y-intercept divided by some constants. So we do this for each xy, we fit this line, and we are able to get the map on the left here. So this is the measured EL gap as a function of x and y, and you can see a clear variation in thickness with x and y. It looks maybe kind of planar. You can see a clear gradient from thicker on the upper right hand to thinner on the lower left hand. So we fit it to a plane, and then the fit to a plane is what you see in the middle. The residuals are on the right, which is just the difference between the measured values and the planar fit. And the residuals are all relatively small, all less than a millimeter. But there is, it looks like, is maybe something going on the edge here. The residuals look larger there. Well, no, actually just that the error bars are also larger on the edge. So when you divide by error bars and plot this in terms of sigma, the discrepancy goes away. So the deviation is consistent with what we'd expect from an EL gap variation of around 24%. That is 1.2 millimeters between 0.5 centimeters and 0.62. And the pattern of errors, more red and blue towards these edges, indicates possible smaller, higher order curvature, but it's all under 2 sigma. And this level of variation would be expected to give a light yield variation of 20%. So it's very important to observe and be able to correct for this. So the next and last thing I'll be talking about is finding the Z position of events by studying diffusion. So S1 is traditionally what is used to determine the Z position in TPCs. As described previously, you have your S1 signal, you have your S2 signal, they're separated by some amount of time, you have a known drift velocity, and so the time difference between these signals gives you your event position. And you need your event positions, in particular, to do lifetime correction. Now, the S1 comes from PMTs in NEXT, but the PMTs are somewhat radioactive. They're going to be a leading contributor for larger experiments to our radiation budget. So we would like to get rid of them, replace everything with just use exclusively SIPMs. However, SIPMs have more dark noise, and there's a possibility we would not be able to detect the krypton S1 if we used only SIPMs. So the question is, can you extract the Z position in an alternative way with no S1? Well, Luckily, the events, that is the electron cloud that is produced, diffuses as it drifts. And so events that occur deeper in the detector are wider. We retain some Z information. So how do we
Sorry,
quantify?
1 minute.
1 minute. Okay. How do we quantify this? So the diffusion of the contributes to the width of the events, which we can quantify with the RMS of the event. You can think of it as sort of being like the standard deviation of the distribution. It's defined in the normal way. And we expect the RMS squared to increase linearly with depth from diffusion. So you can see some example events with their RMS as shown here. Indeed, when we plot for many krypton events, RMS squared versus Z, we see the expected linear trend. Allows us to convert between Z and RMS and get Z from RMS without needing S1. Does this have an impact on the energy resolution is the key question, though. So we looked in next white data that's just finished running. We're looking at the resolution in krypton, and you can see that on the left axis and extrapolated to Q beta beta on the right. Each of these points represents.
I'm sorry, you're out of time.
Okay, I'll just do one more minute cutting into the questions. So essentially what we can see is when you look at different volumes, there is not a significant degradation. You see, the Z from diffusion lines are slightly above the Z from S1 line. The resolution is slightly worse, but it is all less than 0.1% at Q beta beta. So ability to detect krypton S1s, the ability to run a detector without the ability to detect krypton S1s appears feasible, although there is the possibility that larger S1s could also not be seen, and we need to do some ongoing work to look at doing this with higher energy. So I'll just put the conclusion and let people ask questions, but the main conclusion is, of course, krypton is a very powerful tool, allowing many interesting investigations of the next detector. Thank you.
Thank you, Jonathan. So any questions? Any questions for Jonathan? Please raise your hand. All right, so seeing none, I think I'll ask a question. So have you done any, I'm just curious if you, how different is this diffusion as a function of Z in gas, since you're using gas versus liquid? Because I've seen liquid models, for example, for the Lux and Xenon 1-ton S2 only analyses, stuff like that. Is it better, harder? What are the differences between liquid and gas for the diffusion versus Z?
Yeah, I'm not super sure. Everything that we have has been exclusively gas, so I'm not so familiar with what the diffusion looks like in liquid. Yeah, I can say that the width squared being proportional to Z holds very, very well in gas. There's some additional characterizations we've done showing that basically the quality of that relationship gets basically linearly fuzzier, gets worse as you go deeper into the detector. The uncertainty gets larger, but in general, we've found that that diffusion model works very well. I can't really comment on how well that compares to the situation in liquid.
Okay. All right. Thank you for your talk, Jonathan. We're going to move on then. Thank you. So next. Our speaker is Tyler Anderson, who will be speaking on salting as a bias mitigation technique in LZ.
Great, thanks, Matthew. So yeah, I'm a graduate student at Stanford. I work at SLAC with the LZ group. So of course, I should mention, other LZers are talking in the coming days, and I would encourage you to attend their talks too. But my talk's on bias mitigation and specifically salting. So I'll start conceptually. This talk kind of splits into two parts. First, I'll just talk about motivation. And then after that, I'll go into more of the mechanics of how to salt, because that's pretty fun to talk about. So just in terms of motivation for bias mitigation, the whole idea is that, we want to overcome human biases in analysis. And when I say biases, you can think things like confirmation bias. And this is especially important when the stakes are so high, as is true for many of us. And for LZ, we don't want to be using bad analysis or biased analysis to be making bold claims about what dark matter is or is not. And you can look through history to find, plenty of examples of biased analysis, but I'll give one here, which is the history of the elementary charge value or electric charge value, which was first measured by the oil drop experiment, which it did a pretty good job measuring a value 0.6% smaller than what we know it is today. However, what we know it is today lands at about a 5 sigma discrepancy from that value. So the issue with bias doesn't come with that first result, but rather with the following results, as the following experiments were pretty reluctant to deviate too much in their values. So reflecting on this, Feynman said that, when they got a number that was too high above millikins, they thought something must be wrong, and they would look for and find a reason why something might be wrong. But when they got a number close to millikins, they didn't look so hard. So it's kind of an example of confirmation bias. So we obviously want to avoid something like that. And current techniques used in the field include things like blinding, data prescaling, and hidden parameters. But I'll be talking about salting, which is the injection of fake signal events. And this is something that was also used in Lux. And as it was used in Lux, I have this nice picture to kind of give a broad picture of what's going on with salting. So this is our, log S2 versus S1 parameter space where we do a lot of our WIMP search. Each dot represents an event. Most events fall in the electric recoil region, but WIMPs would fall in the NR region, and that's where the salt events in blue are placed. And the idea is that these salt events are injected into your data without anybody knowing, the difference between the black and blue dots. All of the analysis happens, and just before you create your final limit or discovery plots, you reveal which events are salt, remove them from analysis. So as for the physics behind S1 and S2, I'll trust that most of you have seen it, at least in this conference so far, but I'll direct your attention mostly just to the waveform, because that'll be important. For the S1, this initial burst of photons occurs as like a small blip or pulse. There's a gap in time as the electrons drift up, and then you get this larger S2 signal in your waveform that's proportional to the number of electrons created. So with all the motivation out of the way, get to the fun part, which is talking about how we actually do the salting. This is fun to talk about because it's not every day that you're allowed to secretively inject a dark matter signal into your collaboration's data. So to go over this process, here's a broad picture. I'll go more in detail in the future slides, but the basic idea is that to create these fake waveforms, we actually use real waveforms from calibration data that fill out the ER band. So you can look at the cartoon here, where if we want a salt event to go with the blue dot, we find a calibration event in our ER band that has a very similar S1, take its waveform. Then we also find a calibration event with a very similar S2, take its waveform, smash those two waveforms together, and then you get one waveform that looks like a NR event or maybe a WIMP. You do this for a bunch of different salt. As you take data, you inject these, and then after analysis, you unsalt. So a lot of thought actually has to go in at the very beginning on where we want to place these salt events in S1, S2. So that starts with semi-randomly picking a WIMP model to characterize the salt. And I say semi-randomly because this shouldn't be something that's known by either the people who coded this process or the people who ran the code. And also we don't want to pick a WIMP that we would have expected to have detected already in a previous experiment. Once we get a WIMP model, we can start sampling S1 and S2 values from the WIMP and also from a flat pedestal, which will just fill out the remainder of the NR band, as you can see in the picture. And we also, with each salt event, get a timestamp of when we kind of want to place it in data. Once we have ideas of where we want the salt to go, we start going through calibration data, looking for good matches for those S1s and S2s. So this plot on the right shows matching using a simulated radon 220 data set to verify that, we have pretty good matching between where we want the salt to go and where we can find S1 and S2 waveforms that will match that salt. Once we have identified the calibration events, we chop and stitch them together. So this is conceptually pretty simple. You just chop out the S1 part of the waveform from your S1 calibration event and use it to replace the S1 in the S2 calibrations event. And what you end up with is a nice waveform that looks like it should be a nuclear recoil or a WIMP. You do that for every salt event you generated, and as data is taken, you start to inject these salt events. To inject, we actually replace random triggered events, and these random triggers occur at a rate, an average rate, such that you won't be able to tell if one is missing or not. So as that, you can't be able to identify salt. And along the same lines, you also want to modify any metadata that will reveal these events as salt, or we also remove any PMT signals from PMTs that have died in between taking your calibration data and physics data when you want to do the injection. And that's shown in the plots. The end result is something that looks like a WIMP. So this is one of our waveforms. And we have verified that these waveforms, or we have sent some of these waveforms to analyzers to verify that analyzers can't tell the difference between our salt events and simulated NR events. So just kind of a final example or final verification of our salting process occurred in LZ's mock data challenge 3, which was about a month of simulated data into which we injected 5 salt events shown in the plot. And you can see in blue where we wanted the salt to go, and black where they ended up. We did a fairly good job. In the final analysis, 2 of these landed outside of the region of interest because they were at high energy. They came, from that pedestal. 2 were cut out by the fiducial cut as they ended up near the wall. And finally 1, this guy survived all background cuts, and this champion salt event made it to our final, log S2 versus S1 plot. So now we've come full circle to our final plot here. This was created without anybody knowing that this single event was a salt event. So we can claim success there. And here's the event waveform. So overall, we're pretty confident moving forward. And with that, I think that's everything. So thank you.
Okay, so plenty of time for questions. You ended in ahead of time. So any questions for Tyler? Please raise your hand. All right, well, ordinarily I'd ask a question, but I'm biased because we're on LZ. So I think we'll end it there. Thank you so much, Tyler, for your presentation.
Great, thank you.
So our next speaker is Clark Hardy, who will be discussing light map reconstruction in Nexo with an internal xenon 127 source.
Okay, thank you. Yeah, so I'm going to be talking about some work that I've done with Nexo collaboration on how we might reconstruct a light map in Nexo using an internal xenon 127 source. So I hope everyone got the chance yesterday to see Brian's nice talk on an overview of Nexo and projections for our sensitivity. But in case you didn't, I'll just give a brief summary. So Nexo is a single phase time projection chamber that's intended to search for neutrinoless double beta decay. And we're looking for neutrinous double beta decay in xenon 136. So we use 5 tons of liquid xenon enriched to 90% in that isotope. And our recent sensitivity estimates, which went on the archive earlier this summer, project that we can reach a sensitivity of greater than 10 to the 28 years for almost all of the nuclear matrix element models considered. Uh-oh. Sorry, I'm not able to change my slide, it seems.
We are on slide 2.
Yeah, I'm trying to change it ahead, and for some reason it's not allowing me to.
Try stopping the screen sharing.
I'll just reshare it. Okay. Okay, there we go. It's working.
Yeah.
Okay, perfect. So, I'll just give a brief overview of why this work is necessary. Basically, as you can see from this plot on the right, we have quite a long drift length of 1.2 meters. It's significantly longer than an nexo 200. And this plot is also showing the variations in the photon transport efficiency across the TPC. And as you can see, there's a significant variation. So these necessitate 2 important corrections to achieve our energy resolution goal. One is the electron lifetime, and the other is the position-dependent photon transport efficiency, which we call the light map. So there are a few different ways that we can achieve this calibration. One is to use an external gamma source, which has the advantage of being very easy to deploy. We can basically pick and choose the energies we want, and we don't risk introducing new backgrounds into the xenon. But the disadvantage is that there's quite strong attenuation in the skin xenon, just because we have so much xenon mass that the gammas have to get through. And this also requires us to stop data taking and sacrifice some live time. A good way to avoid some of these drawbacks is to use an internal alpha source instead. And this is kind of our default plan. It gives us excellent energy resolution. We can illuminate the entire detector volume without the problem of attenuation in the skin that we see with gammas. But again, this would cause us to sacrifice some live time in order to conduct this calibration. So that brings us to what we're considering as a potential alternative or a supplement to our original calibration plan, which is to use an internal xenon 127 source. So this source is basically an electron capture to excited states of xenon or of iodine 127. The half-life is 36 days and the Q value is 662 keV. The idea is that we'll mix this uniformly throughout the TPC, aiming for about 1 becquerel of activity during the calibration period. And the nice thing about this is that because we have this long half-life and we can just mix it through the TPC and maintain this activity, we don't actually need to sacrifice live time, provided we don't have such a high rate that we're causing pileups in our data acquisition. And so if you look at the plot on the right here, you can see the energy spectrum with basically 2 clusters of events around 200 and 400 keV. What that translates into in charge and light production is basically these 2 peaks with some of that substructure smeared out, partly due to the fact that we have very close lines getting smeared together, but also just intrinsic peak width due to the recombination fluctuations. The lower these peaks is around 200 keV, which is close to the projected threshold that nexo will operate at. So we're not really interested in that one. We're more interested in the 400 keV peak that is both well above the threshold, but also below the region of interest for our neutrinos double beta decay search. So basically, in order to prove that this would be feasible in nexo, we conducted a test at Stanford. We started by taking some natural xenon in a small sample cylinder and having this irradiated at a nuclear reactor facility. Basically, the amount of xenon 126 in natural xenon is sufficient to cause activation to xenon 127 at a rate that will give us events that we can see when we inject this into our TPC. And so if you look at this plot in the bottom left here, the important thing is that although we get all these byproducts as well, after about 100 days, almost all these have decayed away, and we're just looking at dominant activity from xenon 127, which is what we're interested in. So we had some radioassays done and some germanium counting just to confirm the activity, and we're able to confirm that indeed we are seeing predominantly the xenon 127 without any unexpected activity. So we were able to get some preliminary results in our Stanford TPC, basically just by injecting this in to our recirculation loop. So we use this little sample cylinder with 2 valves and a pressure gauge here, filling this intermediate volume and puffing it in 1 puff at a time into the recirculation loop. And so you can see the plot on the upper right showing basically the decrease in pressure over time as we did this injection in 2 stages. And then on the bottom of that plot, the corresponding increase in the trigger rate that we saw as we started to trigger more on these events from xenon 127. So we've got some preliminary data shown in the bottom right here. And I think you can see pretty clearly that we do see these 200 and 400 keV peaks and the corresponding decay that is a result of the electron lifetime. We do plan on publishing some results showing full calibration of the electron lifetime. But the thing I'm interested in is the light map. If you look at a diagram of our TPC on the left here, you can see that we've got a pretty small SIPM array that doesn't actually give us good enough coverage to do light map calibrations. So I instead focused on projections for nexo and how this might look in a detector with really good light coverage. So basically the problem that I'm dealing with is getting a set of calibration events, which is basically just positions that we've reconstructed and an associated efficiency given by the number of photons detected divided by the expected number for the calibration peak we're interested in. And what I want to do is feed this into some function that's going to reconstruct the light map and hopefully provide something that's continuous and smooth and covers the whole detector. So there are a few ways we could do that. We could use a histogram, which has some drawbacks. One is that the bin size is limited by the number of events we have. And if we have too few events, we get some empty bins. It's also not continuous. We could fit a spline to this data and that works a little bit better, but we also get some noise that doesn't actually reflect the true photon transport efficiency in the detector. Or we could go with the option that I settled on eventually, which is to use a neural net that is specifically designed for this purpose of creating a smooth and continuous light map function. And so in order to basically test this process, I simulated some xenon 127 decays in nexo using our nexo offline simulation package that incorporates a full detailed geometry of the TPC and the NETH software to model the charge and light production. The plot I'm showing on the right here is the truth light map that is produced using the GPU-based Chroma software. It basically tells us our best understanding of the true photon transport efficiency throughout the detector. And basically by binomial sampling the number of detected photons for each simulated event and adding a Poisson fluctuation term representing correlated avalanches, I can get a set of data that represents the detected photons in this calibration data set. And so I applied some simple cuts to this data. First, it's just a 20 millimeter standoff cut to cut away events from the edges. Since we do have these 2 peaks, only one of which we intend to calibrate on, I applied this diagonal selection cut in the raw detected photons and detected electrons. And you can see basically what the uncorrected light signal looks like. We have this significant smearing effect resulting from the fact that we've got this totally uncorrected photon transport efficiency that varies significantly across the detector.
1 minute.
Okay. And so for now, I am using just the higher energy peak, but if we are able to resolve some of the low energy peak, we could use parts of that as well. So here are some first results showing the reconstructed light map from this data. So what I'm showing here is basically the reconstructed light map divided by the true light map. And so anything close to 1 is good. It means an accurate reconstruction. And I'm showing this for ranges of data set sizes from 1,000 events up to 1 million events. You can see that as you'd expect with 1,000 events, we get worse reconstruction and we get some pretty clear systematic errors. This is basically a result of the fact that the neural net, in the absence of a sufficient number of calibration events, will just default to a more flat light map. And so when there actually are deviations in the true light map towards the corners of the detector, fitting a flat light map to that is going to result in these systematic deviations. But as we add more calibration events to our data set, these start to recede to the point where for the data set of 1 million events, we have a very clean reconstruction, particularly in the inner 2 tons indicated by this dotted line.
I'm sorry, you're out of time.
Okay, maybe I'll lead into question time and finish this up in the next 30 seconds. So basically the takeaway result here is that, as you can see in the plot on the left, we do basically remove these weird deviations that result from the systematic errors I described previously and get a nice accurate reconstruction with larger data set sizes. The plot on the right is basically showing how the light map error term that goes into our energy resolution expression changes with respect to the number of events. And for the inner 2 tons, we do get less than 0.5% error, which is the point at which this term contributes minimally or is basically negligible in our overall energy resolution. So we're not adding anything to our energy resolution from the light map alone. So I think what I'll do is I'll just acknowledge all the work that everyone on the Nexo collaboration has put into this and all the participating institutions, and I'll just leave my conclusions up. And I'll be happy to take any questions.
All right, thank you, Clark. So any questions for Clark? Okay, I see a hand up. So Lior Arazi, please go ahead.
Yes, thank you. This is interesting. I didn't know you were doing this. Just to make sure I understand, you're not using krypton because of your threshold for the energy. You cannot see krypton events.
That's right. Yeah. So we're basically using this because we get it well above our threshold, and it's kind of a nice intermediate between being above threshold and far away from the region of interest.
And
krypton, I guess, would be below threshold.
And what sets the choice of 1 becquerel? Can you work at higher rate, or this will interfere with your physics data taking? Yeah,
basically we just we need to keep it low enough so that we're not causing pileups, and so one becquerel is not a hard number that's a result of a lot of study. It's kind of our benchmark at this point, and I think we'll look into this further and kind of figure out where our true limitation is. But we basically just don't want to get too many events that will interfere with data taking with the physics data.
Okay, great. Thank you.
Thank you.
Any other questions? All right, looks like no other questions. Thank you for your talk.
Thank you.
Okay, so our next speaker will be Michael Coleman, discussing optical modeling and position reconstruction for DarkSide 20K.
Hi, today, as you mentioned, I will be discussing the DarkSide program's effort to search for high mass dark matter with 2-phase liquid argon time projection chambers. And I will specifically be focusing on our next generation detector DarkSide 20K. I'll discuss the optical model we use to describe scintillation in liquid argon, as well as how we simulate events, and our work on algorithms which are used to reconstruct XY positions for events. So first, here's an overview of the detectors of the DarkSide program. The first physics detector of the program was DarkSide 50, which started taking data in 2013. And after 5 years of data collection, set world-leading limits on dark matter interaction cross-sections. These have subsequently been improved upon by other experiments, but we are currently analyzing more data to set those limits. So stay tuned for that. The next generation experiment is DarkSide 20K. And this is projected to start taking data in 2025. So DarkSide 20K will be installed at the Gran Sasso National Laboratory in Italy. This detector is designed to operate for at least 10 years with an irreducible background level of less than 0.1 events for the total exposure. The TPC shown here will be filled with low radioactivity underground argon, which will allow us to achieve that background level. This will be surrounded by a VITO, which includes gadolinium-doped acrylic panels. And this is all installed inside of a large cryostat, which may look familiar since it's based on the one that's used for protozoos. So we've incorporated a lot of novel technologies into DarkSide 20K, some of which are the TPC vessel is composed of acrylic, and we are using reflective panels that are made from an enhanced specular reflector film, which is called ESR. And this is coated with TPB, which shifts the liquid argon UV scintillation light from 128 nanometers to the blue visible regime. One significant feature of DarkSide 20K is the custom silicon photomultipliers that we've developed specifically for this experiment. Each photodetector module shown here is composed of a 5 by 5 centimeter squared array of silicon photomultipliers. And we will use a total of 8,280 of these photodetection modules throughout the detector, split between the top and bottom to detect light from each event. As accurate simulation is crucial to ensuring the success of DarkSide 20K with, based on design decisions and all of these things, a lot of work has gone into accurately modeling liquid argon's response to both nuclear and electronic recoils over a vast range of energies and applied electric fields. Our custom-built simulation framework is called G4DS, and this is based on GAMP4 and implements full photon tracking. As shown here, we can see an example of a simplified version of the geometry just for clarity, and then example photon tracks originating around here, scattering throughout the detector until they are detected at either the top or bottom of the detector. So here we're able to implement a bunch of optical properties, including refractive indices, absorption lengths, scattering lengths, as well as the wavelength shifter and reflector. So in particular, the wavelength shifter and reflector geometry, new measurements were made by the Tupac experiment, which was run by some of our collaborators. And this paper is currently under review. So please do check this out if you're interested. So using DarkSide 50 data, we tuned 20 different optical parameters to fit our Monte Carlo simulation to the data we actually saw. An important thing we wanted to do in this calibration is to make sure that this is that the variables we look at are independent of energy, so we're not biasing ourselves to a specific energy regime. So we look at relative variables, for example, as shown here in this plot, the total light collection efficiency as relative to the center of this TPC. And we look at this as a function of the vertical event position, with 0 being the bottom of the TPC, 1 being the center, and 2 being the top of the TPC. We then also look at another variable, which is the top to bottom asymmetry in the detector, which is the amount of light seen in S1 by the top photo detector array divided by that for the bottom. And so using observables like this, we were able to do a chi-squared minimization over a grid of parameters to find the best fit values. We initialized the parameters from measured or calculated values, and then fit within error to see which are the best ones that fit the data that we actually saw. Another important calibration, which is really important to our Monte Carlo simulations, is the energy scale for liquid argon. As the S1 and S2 responses of liquid argon are nonlinear for non-null electric fields, which are applied throughout the TPC, we parameterize the liquid argon's response with an effective model. So here's a diagram of this model where for a given interaction, we see the atoms are divided into two different categories. One is where we have electron-ion pairs, and the other is where we just have excited atoms. For the electron-ion pairs, the electric field applied throughout the TPC drifts some of the electrons towards the gas pocket before they can recombine, while another fraction recombines with ions, thereby producing scintillation light when it de-excites. More scintillation light is produced by the excited atoms as they de-excite, and together this scintillation light is known as our S1 signal. Now, the electrons that didn't recombine and were extracted to the gas pocket are accelerated through the gas pocket and produce electroluminescent scintillation light. And so then we get our number of S2 photons that are created here. So we've recently updated this calibration using data from DarkSide 50. And so this paper is also currently under review. So please do take a look at that as well. So now that we have a Monte Carlo simulation framework that has been tuned on experimental data, we can then make some important design decisions for our DarkSide 20K experiment, as well as test some of our reconstruction algorithms for the experiment. So to create a fake event, we start from G4DS by simulating the physics processes of different interactions in the detector. And then we simulate the optical photon tracks until they reach the photosensors. We then apply a Monte Carlo that encapsulates the electronics response, so the silicon photomultiplier response to detected photoelectrons, along with the transmission and the digitization of the signal. So shown here is an example silicon photomultiplier waveform for a single photoelectron that we've simulated and then started to process. So then with the reconstruction, we can process these waveforms and determine where these photoelectrons are. So a hit time and then a number of photoelectrons detected as well. Once we have these hits, we can group them into S1 and S2 signals. And once we have S2, we can apply an XY reconstruction algorithm to determine where in the TPC this event occurred. So shown here is an example of a simulated S2 light pattern. So we primarily use the reconstructed event positions for fiducialization. So a lot of the backgrounds are near the surfaces of our detector. So we define a region in green, which contains our 20 tons of active liquid argon. And we refer to this as our fiducial volume. And so by doing this, we're able to cut a large portion of events and reach our desired background levels for the exclusion limits that we want to reach. So shown here is a simulation of the radiogenic backgrounds before any cuts are applied. So to prevent leakage into the fiducial volume, namely if we misreconstruct a position.
Sorry, you have only 1 minute left. Sorry,
okay,
1 minute.
So if we misreconstruct these positions, they will increase our fiducial volume rate. So just an overview of some of the algorithms we've tried. One is using just a simple 5x5 square PDMs, and then a simple center of gravity method for this. Another method uses machine learning algorithms, so namely the DB-scan algorithm, to locate dense regions and expand clusters from them. And we've also investigated using neural networks, so specifically convolutional neural networks, which use the same principles as picture recognition. So looking at the projected XY resolution using these different methods, we see that we improve the projected XY resolution using the DB-scan algorithm by almost a factor of 2 over just the simple standard method. However, DB-scan performs more poorly at the corners, so this is something we're actively working on improving. One of the advantages of convolutional neural networks is that they can perform well even with conditions of saturation or inactive PDM. So if we somehow lose a connection to one of the photodetectors. And we see that we reach the required XY resolutions even under these conditions. So to summarize, we will be searching for high mass dark matter with the DarkSide 20K experiment. And we use a dedicated Monte Carlo to simulate these events, which we've tuned on DarkSide 50 data. We expect better than 1 centimeter resolution for the XY reconstruction, which is sufficient for our background requirements, and that machine learning techniques, specifically convolutional neural networks, show great promise for dealing with saturated or inactive channels. I apologize for going a bit over, but I can now take any questions.
All right, questions for Michael. All right, I don't see any, so I think I'll ask a question. So one of your points here is a projected XY resolution of less than 1 centimeter. Can you go deeper into how that resolution, though, depends on the amplitude of the signal as well as the radius? Is there a pretty serious dependence on either of those?
Yeah. Oh, well, so for smaller events, we see that. So for events where S2 is smaller, we see that the resolution is closer to 1 centimeter, whereas for high S2 events, we can do much better than that. So almost 0.6 centimeters, so 6 millimeters or so. So we do see better resolution for larger events. However, for very large events, we can run into the issue of saturation. So where our photodetectors hit a flat level where we can no longer then get a proportional level to how many photons are detected. But then the CNNs have been shown to help compensate for this.
Okay, any questions for Michael? All right, seeing no other questions, thank you, Michael, for your talk.
Thank you.
Our next speaker is going to be Vincent Basque on the measurement of the scintillation light triggering efficiency in a microboon.
Perfect. Let me go full screen. There we go. And you can see the slides changing.
Yes.
Perfect. All right, so yeah, my name is Vincent. Today I'll be talking to you about the measurement of the scintillation light triggering efficiency in microboon. And here are just two very nice pictures of microboon. So this is inside the cryostat, and this is one of the events that we see. So microboon is part of the short baseline program at Fermilab, which consists of 3 LRTPCs placed at different baseline along the booster neutrino beam that's produced at Fermilab. So microboon sits quite in the middle, around just 0.5 kilometer away from the target that we see on the far right. Microboon is, it's a rectangular shaped box that we can see here. This is the TPC, about 10 meters long by 2.5 and 2.5. So it's been running since 2015, and its main goal is really to determine whether the mini boon excess that was observed, which mini boon was just behind where microboon is located, is more electron light or photon light. But at the same time, we'll perform our cross-section measurement of neutrino argon for LRTPC, especially R&D. So microboon, obviously, being a LRTPC, will detect the UV light, and it does this with 32 8-inch PMT that's placed along the z-axis. You can see them located in rosette formation all along the z-axis. What you can see in the picture are our echolith plates that are painted with TPP and polystyrene. So the PMTs are located just behind those kind of like shadow or hazy sunglasses. The PMT were formed or record without threshold in coincidence with the trigger beam that we obtain from the auxiliary division. So we know when the neutrinos are coming. And we have a sampling of 64 megahertz with a 60 nanosecond electronic shaper response. So what do we use primarily the light in microboon for is really to identify and time TPC event. And we match those with what we call light flashes. So what it gives us a T0 for the X position, so for the drift position, and that allows us to do rejection of cosmic. There'll be a very nice talk tomorrow on time and resolution in microboon, so please stick around tomorrow. Obviously, the light yield is dependent on where the light generates from where it's detected. So here we have just a light map of the microboon detector, which is the TPC is like this square box, while the cylindrical shape is the cryostat. So this is calculated using like convolution of electrical field that we have across the detector, the geometrical acceptance of the PMT, and also just the light propagation that we obtain from GEONT. And what you can observe is because microboon has an opaque cathode, which is located on this side, and a semi-transparent anode, which is located on this side, and field cage, which is all around, we see really that we can obtain light behind the anode and also on the top and at the bottom of the detector. So obviously, when we have neutrinos that interact into the RTPC, the PMTs will see an increased amount of light, and then we can use this light that we see to time match it with the beam spill they obtained for the exterior division. And that provides us a trigger information of these events. So an example that we can see is on the right here, where you have a BNB or a beam-induced neutrino, where we see a coincidence in activity on all the PMTs, so big jump in ADC and of the waveform, whether that's within the beam spill, while for any other type of interaction or nothing, no interaction rather, we don't see any of these sorts of things. So we do this by collecting the light in the first, just the first 100 nanoseconds or so to give us threshold on threshold condition on our PMT to trigger on. And that light provides the trigger, obviously, and the timing is complementary to the TPC information. So that gives us our T0 and X position especially. And the triggering, especially in time with the beam spill, can allow us to distinguish between a true beam event or a background cosmic event that we get a lot because we're at the surface. So obviously being on the surface means that we collect a lot of data, but not all, just we can't process and save all of it. Especially since a lot of it is empty triggers, so we don't want to focus too much on that. So what Microboon does, it uses two types of software triggers based on the amount of P that we measure by the PMT from the prompt light in the beam window to say if we reject or keep these events. So the first one is like quote unquote an online trigger. So we need at least a 5 PE to not be rejected by a BMB trigger. So you can see here, as we increase the amount of P threshold, we also start rejecting a lot of the beam spills, but most of these are actually empty from the beam because we only see about 1 neutrino every 1,000 spills or so. So we're just getting rid of empty events. And then we have a offline, if you want, requirement to have 20 PE, which is what we use in current analyses, and that's further reduce the computing load. So that leads to a very important question: is what is the 20 PE triggering efficiency? This is what I'll try to be out. This is what I'll be answering today. And also see this measurement, I'll compare it to Monte Carlo to test what our light propagation model in Microboon. So to do this trigger efficiency measurement, we wanted a very specific sample that has certain criteria. We wanted something that had low energies, especially in the low energy excess, that were well defined, and we had a lot of these events. We wanted simple topology, especially we just wanted a mid energy deposition. We didn't want anything that had bursts of light that could bias this measurement. We decided to have our events at the furthest point from the PMT, meaning they have to be at the cathode, because from here you have the most of the propagation of the X direction. We also wanted our events to be independent. The selection to be dependent from using scintillation light, which is not what a normal analysis do. It uses the scintillation light to match with flashes. So what we decided to do is use cosmic ray muons that pierce the cathode. So we want cosmic ray muons that enter the TPC through the top or through the side and then exits, so that we don't have problems like Michel or Bragg peak. And with this, that allows us to select our sample by tagging with the CRT. So the two selection cut that derives from this is we want to make sure that our CRT hits can be matched to TPC tracks, and then we get a T0. So here I'm just splitting the sample into two for tracks that produce more than 20 PE, which is well distributed. There's nothing here. But then for tracks that produce less than 20 PE, we have this region of nothing essentially here, which means that these tracks are not producing light in this region, or not enough light rather, which is the sample that we want. While the population just before means that while the track has like 400 MeV, is a track of 400 MeV not producing 20 PE is a bit ridiculous, especially Microboon. Therefore, we know that these events are producing light outside the trigger window. And then when we apply these to have in this range that we see here, and we apply this to the reconstructed start or end position to get our both types of tracks, we obtain a very nice narrow and no tail on the distribution at the cathode. And that gives us a purity of like 97%. Also, because Microboon has a certain region of unresponsive wires, which affects the amount of charge that we measure. We devise a cut to try to remove those. So what we calculate is just the energy from the charge and the energy that we get from the track length, and we calculate this ratio, which we plot here. And then we just fit a symmetric Gaussian and look around where the mean and take a 2 sigma region here. So basically we want to remove any of these, especially here, because this is where no charge is reconstructed. So that gets rid of reconstructed failures, but also events that are in a region where there's too many unresponsive wires. So what does our sample look like? So this is a full sample that we have. And after passing the selection cut, we obtain only the blue types, the blue lines, which mean they're crossing the cathode.
1 minute left.
Crossing the cathode, or are in time with the TPC. Well, the red ones are not. So what we do then, we have to calculate the efficiency. So that means just asking a question for every track: is a track producing less or more than 20 PE? And then we just start counting the tracks, and we do this for every bin, and every energy bin. So this is the end result. That after we ask all our sample and our tracks in our sample if they make if that more than 20 PE, we obtain this triggering efficiency here. In blue we have the data, and then in orange we have the Monte Carlo. So there are some differences in the Monte Carlo. While they are covered with the very preliminary systematic error, we're still currently investigating. But this is showing that relatively good agreement, and especially above 200 MeV, we have a flat 100% efficiency, which is where the LE or the low energy excess lays. So we have presented this data-driven prompt scintillation light triggering efficiency microboon. The calculation efficiency is done at the worst case scenario where there's the least amount of light in the detector, which is at the cathode, and we see that we have a near 100% efficiency triggering rate for the tracks or the event approaching 200 MeV or more, which reassures us that for LE type events we are triggering on them, so we're not losing any of these events. And we have shown the preliminary systematic, which is based on what we observed between the data and Monte Carlo, and full assessment is currently underway for publication in the not so near future, or in the near future rather.
All right, thank you, Vincent. Any questions for Vincent? All right, sorry, seeing no questions, we're going to move on to our next talk then. Thank you, Vincent. So our next speaker, Tyler, will be talking about the measurement of the total neutron cross-section on argon in the 30 to 70 keV energy range. All right, take it away, Tyler.
Okay, so my name is Tyler Erjavik. I'm a graduate student at UC Davis, and I work under Professor Melev Hantich. And today I will be talking about a measurement we did of the total neutron cross-section on argon in the 30 to 70 keV energy range. So our experiment is called the Argon Resonant Transport Interaction Experiment, or ARTI for short. And we aim to precisely measure the depth of the anti-resonance at 57 keV and the total cross-section of neutrons in argon. So why do we need to do this? Well, the total cross-section of argon is contested between a theoretical evaluation via the evaluated nuclear data file and experiment. So there was an experiment done in the 90s by Winters that used a pressurized argon gas target with a column density of around 0.2 atoms per barn. And that may have not been sensitive enough. So if we look over here to the right, we have Winters data in blue and the ENDF data in black. And there's roughly an order of magnitude discrepancy between the cross-section at 57 keV. And you might be like, okay, well, why is that important? They're relatively close, right? Order of magnitude. Well, the knowledge of this parameter is of the utmost importance whenever argon is used as a target or shield, such as the case in dark matter and neutrino experiments, such as dark side 20K or DUNE. And Where this discrepancy comes largely into play is that the mean free path of a neutron between the Winters, if you're using the Winters data and the ENF data, is roughly 5 meters and 30 meters respectively. So this determines whether or not any background neutrons are going to just wander all through your detector, or basically are going to stop closer to the periphery. So it's important to understand how neutrons transport in liquid argon. So first, in order to do the RD experiment, we need a neutron beam. So we basically use a neutron beam at Los Alamos National Laboratory at the Lujan Neutron Scattering Center. So here is basically a schematic of the center. We're using the orange beam line. So neutrons are first created via spallation of a 800 MeV proton beam, accelerated via a LINAC upon a tungsten target. And then the neutron flux is basically moderated via a liquid water moderator and also a cadmium filter, whose primary purpose is just to reduce the number of thermal neutrons that swamp our DAC so we can reduce our dead time. And then down here in the middle, about 30 meters, is our target hole, where we set our RD vessel, our RD target. And then the neutrons, if they survive and get all the way down to the end, they're eventually captured on a lithium-6 class detector, where the neutron hits lithium, pops out a helium and a hydrogen. We know the exact the Q for this reaction, and then we get scintillation light that's captured by 2 PMTs. So let's go on. I'll talk a little more about the exact RD target. So the RD experiment and target utilizes a method that's called neutron time of flight spectroscopy. So it essentially just is, so a time that a neutron takes to traverse some distance L is dependent on their velocity V and therefore their energy. So this is basically just standard kinematics. But what's not standard kinematics is that these neutrons can be delayed through moderation, capture, or scatter as a function of their initial kinetic energy. And this is largely enveloped in the parameter of the total cross-section. So just to go over the time of flight. So time of flight method. So neutrons are created. They go down a vacuum beam pipe, hit a collimator. They go through our RD target, potentially scatter or capture, hit another collimator, go through another beam pipe, and then eventually hit a lithium-6 detector. So that's basically what time of flight entails. Now I'll talk a little more about what our RD target or our RD vessel is. So it's 168 centimeters long. And when we fill it with liquid argon, we have a column density of 3.3 atoms per barn. And this is specifically targeted to look at the energy range that we're interested in, which is 30 to 70 keV. Now, a particularly interesting thing about the RD target is that it's only foam insulated, not vacuum insulated, and it's also not pressurized. So this means that the argon, the liquid argon, is going to boil off, which not only means that we have to refill it every hour or so, but also the fact that there's going to be some gaseous argon in the liquid mixture. So that'll come into play a little bit later. So, but first, before we do any calculation of the cross-section, we need to calibrate our energies. Because again, there's a moderator delay and other factors that can delay neutrons that are not what we want to look at. So how we do this is we identify resonances of cadmium, larger resonances of argon, and also aluminum in basically the beamline. And we basically extract their energies from ENDF. So then once we have that, we can basically correct the measured time of flight that we get by subtracting a median moderator delay, which is from the water moderator, for some provisional path length. And then we can basically just plug that in and perform a fit for additional delays here, which are just TD. These could be from cable delays, pulse width spread, or any other sort of delays that, so we just kind of lump them all into one parameter and we fit. So we're able to basically get a nice fit with our path length that a flight path that agrees, and then also a delay of around 420 microseconds. So now that we're all energy calibrated, now we can go on and attempt to calculate our total cross section. And in order to do this, we need to essentially, we need to get the transmission coefficient. So the transmission coefficient is just a ratio of number of neutrons that do not interact at all along the beamline or from the, or do not interact at all with the RD target. So in order to do this, we need both a target in and we also need a target out. So the target in is going to be full of liquid argon with a density of rho n, and then the number of neutrons that we detect at the detector are n. Similar thing for the target out, just we are using gaseous argon at atmospheric pressure for the target out. So we can define the transmission coefficient as just the number of neutrons that we detect in each case minus their background, multiplied by a scaling factor, which is just essentially takes the place of the flux of neutrons that are created from the beam. Now I want to talk a little bit about, or actually, so then once we get the transmission coefficient, we can smack it into a natural log, divide by the column density, where the column density is defined over here. And the important thing to look at is the rho in and the rho out. But really quickly, the backgrounds, how do we get backgrounds? Well, the backgrounds are basically, the dominant backgrounds are from neutrons which scatter multiple times. So they might come down, bounce out of the beam line, and then scatter, kind of ricochet, pinball, and then end up back in the detector. So we basically need to determine both our backgrounds. And then also, as I mentioned, because our target is not completely liquid, this rho n. Okay, so how we estimate the backgrounds is we essentially use the black notch method. And this essentially just, so if you have a high cross-section resonance, this creates a valley of low event rates. So we can assume that any events that fill at the bottom of that valley are due to background.
1 minute.
Or else, so then basically we can go ahead and we can get our background for gaseous argon, which is out, which we use aluminum to essentially induce those black resonances. And we assume this is flat. So this is this line right here. And then for liquid argon, or the target in backgrounds, we just use regions of low transmission given by this exponential decay here, or by this line here. So we're able to obtain our backgrounds as a percentage of our event rates. And then, so we got the backgrounds, now we need that rho n. So again, RD's open design allowed liquid argon to boil, thus creating some gaseous argon into the mixture, which lowers our column density. And we needed to measure this. So we measured this at Davis by basically setting our RD vessel on a precision scale, filling it with liquid argon and logging mass and volume boil off. So over here, you can see kind of pictures of us doing that, we kind of tinted it to prevent ice buildup. And we found that despite differing atmospheric conditions between Davis and Los Alamos, which is at 7,000 feet, the boil rate was approximately the same. So we were able to then go ahead and get the density in of target N, which basically correlated to around 6% fraction of gas. So those are two of the major systematics that we had to deal with, but there's a whole bunch more. Again, I mentioned that ice buildup on the target is unavoidable. So during our beam runs, we had ice that built up on the target windows where the neutrons would enter the target. So we were able to basically fit and set a constraint on that. Additionally, 2 meters of beamline was outside. So this was subject to the harsh New Mexico mesa atmospheric variations, and we were able to set a systematic on that. There's a bunch of other systematics that we basically detailed. I'm not going to go through them, but these are the major ones. Other uncertainties that we had, we determined to be negligible. If you have any questions, feel free to ask me about it. As a last kind of check before we got our cross section, we wanted to verify the RD setup. So we placed a precise dimension of carbon via graphite into the beamline and basically calculated the transmission coefficient. So if you were to get for this thickness of carbon disk from E and DF, the expected T in our ROI is 0.72, and we measured 0.73. So they're in very good agreement. And then finally, we get to our results. So over here are our results in solid blue. The Winters data is in red. So we're able to basically identify a very good dip here at 57 kV, and there is a paper in the works. So stay tuned. And then I will, because I'm virtually out of time, I will basically just end with my summary slide. So I will basically open up for any questions here.
Thank you, Tyler. So any questions for Tyler? I think people are tired. You're the last talk, right? So I'm gonna ask a question then. So this is pretty, I think, this came up earlier. It was the idea, we have experimental bias, right? Like something was measured and then something else people were trying to produce earlier. So I'm wondering, do you have, given this great work you're doing here, do you have hypotheses on what caused the discrepancies in the previous measurements?
For the previous measurement via Winters was simply because they didn't have a thick enough target. So they weren't able to resolve lower. So in the, let's see. So in the region of, so if you look at the total cross section of argon, it's largely like many orders of magnitude above the region that we're looking in. So because they use such a thin target of a column density of 0.2 atoms per Barnes, they weren't able to really notice anything, or they weren't sensitive enough to low cross-section features. So that's why we upped our column density to 3.3 atoms per Barn, which allowed us to resolve this much better. Does that answer your question?
Yes, thank you. Any other questions for Tyler? All right, so that ends the session early, 10 minutes.